Hi everyone, welcome back. If you want to head on down to slide 3 and share with us any successes or celebrations, things that have happened recently in the last 24 hours or so. Alicia, it's the same link as past sessions, but I'll go ahead and copy the link for you again here and post it in the chat box. So we'll get started in about 2 minutes. If you have some successes and celebrations to share, go ahead and put them on slide 3. All right, everyone, welcome to Synchronous Online Teaching Strategies, Part 3 of 5. So excited to be back with you all today. And as a reminder, if you want to use any of these templates or slides, they are available on my website. And at the end of the session, I'll have the 5-hour series of all the ones that we've done recorded, and I will work with people in your county to figure out where they want to store those. So you'll have video of it as well. On slide 3 are our successes and celebrations, and let's see who has the Teacher Achievement Award. Tell us a little bit about that.
That's just our honor graduates every year. They each get to pick one teacher to say a few words about that meant a lot to them. And this year we didn't get to do the banquet because of the coronavirus. And I got the plaque in the mail, and it was one of my cross country runners had picked me, and I also taught her statistics. And so I've known her since she was in 6th grade, so it's made my day.
That's wonderful. That's what we're here for. So congratulations. That's awesome. Sure, it's the same link. It'll be the same link every day, but here it is again in the chat box. Who's learning to propagate rosemary and lavender? Sounds like you're going to have a nice smelling garden.
Thank you. I just cut some clippings yesterday and put them in some soil and some Ziploc bags. We'll see how it goes.
That's interesting. I only get good rosemary when I buy it already all super duper sprouted. I can keep it alive at that point. Um, cool. Someone sold their annual herd. How did that go? How long did that take?
That's me, Dr. Wills. Yes, that took about half the day to make it happen, but a lot of work the day before.
I can only imagine. Um, yeah, up here in Fairfax, I don't quite have the space for that. But as some of you might know, I grew up in Spotsylvania, so I know that's pretty close to your gal's backyard, and know the difference once you get out of this like Northern Virginia little area. So, alrighty, let's roll right into our activities for today. Here's the overall goal. We are going to look at doing a routine that can be a quick 5-minute warm-up launch into your lesson. We're going to complete a rich task. And the idea behind this rich task is that you will have about 20 minutes to work on only one math problem. And part of that time, you're going to find a lot of different ways to represent it. And then we are going to hold a whole math conversation to unpack some really big ideas around that rich task. And then we'll kind of move it into a more organized way. How might you use this in your classroom? And then sum up for the day. So I hope that what we're doing today is applicable to all of you, and you'll be able to get some ideas from it. So let's jump right in on slide 4. I'm going to ask you to go on up there on that continuum, grab a text box and put any number you like, and then move that down to the continuum somewhere between 3 and 5. Feel free to get fancy with your text boxes. I always encourage students to personalize things. Where does it lie on this continuum from 3 to 5? Those are my endpoints. I see a lot of people writing rational numbers, and looks like we're getting close to some irrational numbers. Think about other ways we can write numbers. They're not always just in decimal form. And in mathematics, we don't always have the solution as a single number. And I'm going to encourage you to also use only words in some of these. What might you write in terms of words? Oh, you got someone who wrote 4.5. As long as there's still boxes up there, keep grabbing them, keep trying to use them. And I'm going to call on a couple of people to kind of explain why they put their number where they did. And we'll start with this fraction, 22/7. If that's you, would you tell us why did you put that really close to the 3?
I did 22/7, which is basically 3.14 on, and that's very close to 3 because 3 times 7 is 21, and 22 is really close to 21, so that would make my decimal really close to 3.
I love those benchmark numbers there. Lovely. Over here, way over on the 5, I've color-coded it yellow. Who wrote almost but not quite 5? And why does that belong over here?
I wrote that. You wanted words. That's what I went for.
Cool. Excellent. We could get into some amazing topics about limits and things with words like that. So that's going to lead us into higher math. I love this one. All righty, we're getting some really cool stuff now. I just highlighted one of them in yellow. Let me move this other guy out of the way a little bit. Whoa, there we go. Who wrote the number of Beatles in the band in 1964, and why did you have to write 1964?
I wrote that because there were 5 of them for a while before they got popular, when Stuart Sutcliffe was in the band.
Very cool. All right, now I'm going to throw the pedagogy out at you all. Obviously, we could put numbers here. Is there anything else we could do with this template, this idea of a right and then move it down to a continuum? How might you use this in your class?
This would be great for doing probabilities. I mean, you could have a range from 0 to 1 and have probabilities of different events. Be awesome. I don't think it'd be good. Oh, you can hear me. All right.
Absolutely. Yeah, probability. Austin?
You could try to get them to use only like objects, because I was just thinking like a square. You know, you could do the length of one side of a square, or just something that would an object that would represent a number between that, just to kind of get them to think a little bit abstractly.
Ooh, I could really see that being used in volume. You know, if you had 3,000 on one side, 5,000 on the other, there's some apps where you can make these cool volume things. And ooh, I like that. I'm going to use that. What else? I see someone wrote fractions, decimals, percents, ordering them. Thanks, Tina. And then one other thing I like to do is ask my students to get really crafty. Think of their own continuum and what do they think we should use in our class, and I'm going to pick the top 3. And so then the kids end up doing my work for me, like that side of it. But also when they are showing me what they're thinking of, they usually show me a little bit more mathematics than I might have realized that they could have done. So there's some tips for you there. Alrighty, come on down to slide 5. It was our little warm-up, just a little routine called Continuum. We chatted about these math teaching practices on our first day on Monday. This is what the National Council of Teachers of Mathematics talk about in terms of the 8 math teaching practices, things that make it so that students are successful in mathematics. And you're going to see all of these today. You're going to see that I have a clear goal. You're going to do a task that involves problem solving. We are going to connect mathematical representations through meaningful discourse. At the end of this, the whole point of doing this is to have a great discussion. You'll hear me pose purposeful questions both in your small groups and in the overall chat. You're going to look at this problem, and while some of you might feel like you can just go right to the formula and know what that looks like, I'm also going to push you to think about conceptually. How might this work? Why does the formula do what it does? And I'll support you in that productive struggle. So this is what you'll see today, and I have a problem-solving oath on slide 6. I'm going to ask you to take a look at this. This is the problem-solving oath I give all my students, regardless if they are really little in the elementary school, if they're in middle school, high school, or teachers. I'll ask you to read this, and if you pledge to do this, type your name in the chat box. Look at all those great problem solvers we have. Wonderful. Please hold your colleagues accountable for these things. You can even say, oh, wait, remember, she wanted us to make mistakes. We don't have any mistakes on our slide. Let's think of another way. Or let's think of some manipulatives that we could use. So that's what we're going to work on today. Your groups are the same as yesterday, and if you're not on the list on slide 7, go ahead and add yourself where you're likely to be applicable. And then come join me on slide 8 for our task. So this is the math task that you're going to work on today. And it says Jordan is designing a diorama of Chichen Itza, a Mayan pyramid. Chichen Itza has staircases on all 4 faces of the square pyramid. Jordan is using wooden cubes to create the staircase. They notice a pattern and was able to calculate the number of cubes needed for 20 steps. They explained the pattern to their partner Julio, but Julio saw a different pattern. Your job are 3 steps. Describe 2 different ways that the students could visualize that pattern. Use both visualizations to calculate the cubes needed for the 20th step. And then think about how many steps do you think are actually on one side of Chichen Itza? And how many cubes might Jordan actually need to create a perfect replica? So you have 2 pattern questions first, and then you can get into that real life scenario. For those of you who like to incorporate literacy in mathematics, I always, even when I was teaching middle and high school, I liked to bring in picture books. And this one is a cute book that Eric Carle does, and the pattern appears there with animals. So a nice little addition. You all will have space on the slides below 10, 11, 12, 13, 14, and 15. To make as many representations and visualizations as possible. I will be in your breakout rooms to continue to probe you to think differently, to think maybe of ways your students might do it, of ways that you're thinking about do it, and also to ensure that you're thinking about, boy, could I make mistakes here? Like, how might I do that as you're going through them? Alrighty, so one more. I'm on the breakout rooms. Give me just a minute to finish that up. All right, the breakout rooms are available. Again, I will walk you through it, but if you already know what to do, you can head on down and move into your breakout rooms and start working with the people in your group. All right, for those of you who are looking for what to do, you're going to need to move over to Blackboard Collaborate and click on that purple chevron at the bottom if you don't already see the chat box and the attendees. From there, you're going to scroll way below the attendees and you will see the box move in. And I'm going to share my screen. This is probably better to see visually. All right, you can see my screen. It looks like a hall of mirrors. At the bottom of your screen should be a purple chevron, or if it's expanded, your choices, and you need to move to the Participants tab. Underneath all of these names are the different groups that you're assigned to. You'll scroll down and you'll click that little teeny tiny green arrow to go into that group. And if anyone needs extra support, I'm happy to. Otherwise, I'll probably just pop you right into your rooms. So Laura, you're group 5. Who else?
Mikey's lost again.
Let's see, Mike, what group are you in? I'm scanning all the names right now. Simmons. Mike,
Must be
do I have you
6.
listed here? Oh, yes. Okay, I see, because it just had a last name. Yes. So, do you see the screen like I do with everybody's name on it?
Yes.
Great. Scroll all the way down and
Okay.
click that little green arrow to like enter the room of group 6.
Gotcha.
Nice job.
Add one block to each column to show increase of effort. All right. So then use both visualizations to calculate the number of cubes for 20 steps.
Hi there, group. I see somebody knows something about triangular numbers. Why do you have that visual there?
We just recognized that's what we were dealing with. But I guess that just shows the numbers in the first few numbers in the pattern.
Cool. And it's interesting because sometimes students will see that kind of triangular pattern, but then how do they visualize it? Because in this story we had Jordan and Julio, and they were looking at the pyramid, and do they see the triangular number because they're like scooting over the blocks, or they flipping the blocks, like 120 degrees? So kind of think about how they might be visualizing it too.
So like if you were to look at the pyramid, it'd be like one face of the pyramid, right? Like
Yeah.
Yeah, man, it just makes me think of Minecraft again. Like if you were going to build the steps, how many blocks would you need to build the steps?
Yep.
Okay, I better have I'm going to build the steps that are 5 high. I better have 15 blocks of whatever I'm building on.
And I like how you all have decided to put both the function and this recursive one where you say like take 1, then add 2, then add 3, then add 4. And we know where students are going and like why they need that idea that take 1, add 2, add 3, add 4. But what might you do in the situation if a student can't get past the add 1, add 2, add 3, add 4? They can't quite get to that formula. How might you support them there?
We could do visual aids, like we could do hands-on type things. We could have them actually physically hold blocks or algebra tiles or something to show what's happening each time.
Yeah, you could, because you could show them the rectangle would be made by n times n plus 1, and then show them if you took out half of that, you got that stair step thing.
How do you see half?
Well, if you had, like, if you just look at the fourth example of steps, if you did n was 4 and n plus 1 was 5, so you would have 4 across and 5 high. So you could take the exact kind of mirror image top corner off of that and show that it's exactly over that. So you basically got half of that rectangle that's in by n plus 1. Am I making sense?
Well, you can do the n times n plus 1 with like a parallelogram, I think, if I'm thinking of what you're saying, and then base times height would be the area.
I was just on the stair steps. If you build somebody's building a good one there.
All right, so talk it over. You guys have 2 different solutions or visualizations that I'm hearing, and I actually want to bring that out in the discussion. So color code this the way you're seeing it and how you're seeing it getting like chopped up. So let's see. Let me actually undo that real quick. All right, so you now have, if I can move this, come on. There you go. You've got 2 different ones there. You can color code them and chop them up how you see. And I'm going to come back to your group and take a look at it.
So that's the same nest, and yeah, we'll share some pictures with you guys. It's really cool. But anyway, we got 3 babies now that are about 8 inches tall or something now. They really grow quickly. But,
Hi there, team.
Hello.
So you all have this really cool function up here. So 1/2 x squared plus 1/2 x.
Yeah.
How did you visualize what that is? Like, what is that? If I were to unpack that formula and put it into words, where my words were things like cubes, side, tall, things like that, what does this function actually say?
Danny.
Desmos Wizard.
Did you all hear them both?
I guess
I like Tracy's pattern better, but I'm just saying.
X is the row that we're on, and then Y would be the number of blocks to that row.
So if I'm following you, let me see real quick. I made a square because you're mentioning x squared, and I need half of this. So I'm gonna kind of like cut it up, get half of it, and then I also need half of an x. So how long is my x in this model?
As long as one of the sides of the square is right.
Mm-hmm. And this also isn't the only way I can split an x square in half. I can split it in half many different ways. What I'm going to challenge your group to do is figure out how to visualize the function that you all created, because it is a fabulous function, but it is also difficult for some people to visualize. So think about what your x square looks like, where you'll cut it in half, and how 1/2 x is in this whole jumbled thing also. You up for the challenge?
Yes.
I guess.
Awesome.
There we go. 2. All right, that's for 1. Now, how many do we have to do?
It says we have to do
Jordan Division 1 Cures create stair.
Yeah, I'm trying. It's probably something to do with
can't get that one up there.
there's
Okay.
something to do with an exponent, I believe.
Well, I think it's to do with the term.
Oops. All right, let me try to snip this.
Hold on, I think I've got it, but
Okay, so
Hey there, group 2.
Howdy.
This is a really cool visual, this like little Tetris piece thing you got going on where they fit together.
Oh, thank you.
My question to you is, if you're using this formula, which I'll highlight real quick, if you're using that formula, what does it look like before it gets simplified into this pretty one? It seems like there's a little bit of an in-between step from the yellow using that formula to the green.
So the only difference is I'm doing my length times width, but since it's steps, we have to cut it in half because it's not a rectangle, it's half a rectangle, right?
Mm-hmm.
So that's where that divided by 2 comes from. But you just want to see where I put x times x plus 1?
Yeah, I think if you brought that out, because
Sure.
then we could actually make the relationship to that length and width.
Sure.
Yeah, because I'm totally lost.
Okay, let me do it this way. 36, 45, 55, 66, 78, 91, 105. Is that right? 120, 136. Check my math because you know my brain is all over the place.
You're way ahead of me.
153.
Assuming I did my stair step right in my spreadsheet.
And I want to paste. This is probably going to be, oh, nope, it didn't get to. There we go. Oh, sorry, you can mean to paste that over your.
no, I don't care where you put. It's okay.
Well, maybe I kind of like it with the equation in the blocks.
But I can't see. We can't see the equation. I'm going to take out. Do we know what we need? We know what we're supposed to be doing. Draw a picture. I drew a picture. Okay.
Okay.
I'm deleting our instructions.
Gotcha. Okay, so you drew a picture. I did the virtual manipulatives. Who made the table?
Me. Austin, what are you doing? You're part of this group.
I don't know.
So I guess it's quadratic.
Yeah, some kind. It's quadratic, and
Hey, group. I'm back.
Hey, Dr. Rhodes, how are
So
you?
you said it's quadratic, but one thing I frequently hear from students is quadratics only work when it's squared, and this is rectangled. So how is it quadratic?
That's good. We would have to. Well, it's easy to show them that algebraically. Now, geometrically, how do you show them? I mean, algebraically, you could just show them you multiply n times n plus 1, you get n squared. But geometrically, that's a good question. Because there's not any obvious parabola shape in this.
So how might it look on a graph? If you're saying parabola, is this something that you're visualizing on a graph?
Yeah, that's what I'm visualizing in my head is if I were to make a graph of the number of steps against the number of blocks, that would be a parabola shape.
Do you all have a graphing tool that you could use to paste a picture of that graph on your slide?
Where's the Desmos twins?
We can definitely do Desmos and
I was going to
grab
say,
a screen.
Desmos is nice. I just don't know if everyone knows how to use it, knows how to paste it. But if you guys do have a graph, no one else does. And I'm really curious your take on this. Is it a parabola, even if it's rectangled and not squared? Because that one comes up so much with me. I don't know if it comes up with you all.
Let's see.
Welcome back, everyone. Welcome back to the main room. Hello there. Welcome back. Can you believe you spent 25 minutes on that problem alone? It's a super fun problem because there's lots of different ways of looking at it. But now we're going to dive into the mathematical objective of this lesson. I don't know about you all, but sometimes when I teach students how to do things like combined like terms or the distributive property or really any other form of making equivalent expressions, sometimes they look at me like I am speaking Greek. And so one of the things we're going to do today is we're going to talk about ways that expressions are equal to one another, but we're going to do it with the visual component as well. So let's see what that looks like. We're going to start off on slide 11. And the way that I do whole group conversations is there is a very specific part of your slide that I'd like you all to share. And it will likely mean that we're going to get to other parts of your slide also. But for this part, would this group explain what it is that is happening on slide 11 just inside of this rectangle here? What's going on there and how did you visualize this problem?
Yeah, so the way I thought of it was a staircase is literally just half a rectangle. So if we take like one side here, or one piece of a staircase and copy it and flip it over, like that second piece is how the two staircases would fit together to make that rectangle. So that's kind of where my formula started from, just thinking of it as a rectangle and then cutting it in half because stairs are just half a rectangle.
Awesome. So we've got this connection to geometry, this length times width. We can see the two Tetris pieces coming together and then just chop them in half. All right, let's see on slide 15 how what they did is similar and different. So come on down to 15. And they looked at a very similar way of seeing it, but they also have this formula over on the side. And I'm going to ask them, like, what does this formula mean in relation to their picture? So, folks, how did you get from the formula to your picture?
Well, yeah, we actually had the formula before we had the picture, and then we tried to come up with a picture to represent it. So the idea was n times n plus 1, that would be just multiplying two integers together, so that would be a rectangle. And then we were thinking, so how would we divide the rectangle into two halves by dividing by 2? And then we arrived at the same thing. It's going to be an inverted staircase on top of the staircase we had.
So I like the way that that group just said like exactly what the rectangle was. So we have that n times n plus 1 as the rectangle, and then why they're dividing by 2. So everyone else in the chat box, you can confirm that you understand that formula by typing in. If we were to give this lovely image that they have, if we were to give those base and height a value, what's the value of the base? What's the value of the height? You can type that in the chat box. What's the value of the base and what's the value of the height? And simply because of the ambiguity of my question. Some people are coming in with numbers, some people are coming in with variables, and I want students to see that connection, so awesome. All right, then let's take a peek at slide 13. This group saw it a little bit different. in terms of the missing piece. And they've done a really nice job of showing the missing piece with these other little cubes. So they're not seeing the same exact staircase flipped. They're seeing something different. Go ahead and turn on your microphone and tell us, how is their visualization similar? And actually, how is it quite different?
So looking at theirs, I was part of group 3, but looking at theirs, it actually makes sense because it's the previous amount is missing from the next amount. So there's 1 missing from 3. There's 3 missing from the next one. Then that amount is missing from the next one. So I can see that pattern.
Yes. Anyone else?
I guess that made sense to me.
Yeah, it absolutely does.
Well, I think it's really cool because I'm sure I learned this in number theory at some point, but it was gone. But that's illustrating that any 2 consecutive triangular numbers sum is a perfect square.
So now we got that huge generalization there. Way to go.
That's cool.
All right, so here's where the magic of this problem is going to come out. On slide 15, we used group 2's idea of it as just the area of a rectangle divided by 2. So slide 15 says area of a rectangle divided by 2. If that's the case, then what is slide 13 saying? Type that in the chat box. If we were to put it in words, what are they saying here? How do you phrase slide 13? Tim, they are going for a difference. Who else? Put this into words. And so if we tinkered with the formula, in other words, did things like distribute parts of the formula, divide parts of the formula, combine like terms, we would see that indeed whatever formula we made for 13 is the same as 15. But let's go back up to slide 11. Slide 11 had another formula over here. How is that formula similar and different to slide 13 or slide 15? Can you type in words what that's actually saying? If you're someone who likes to voice it out, feel free to turn on your mic. What's the formula in slide 11, that green formula? What's it doing? What's it saying? So we need to find an x squared. That's pretty important just to start off this green formula. So again, those of you who are moving around, we're on slide 11 looking at the green formula. And that green formula, we need to find an x squared before we can continue. Luckily, they drew us a really lovely image, so let's color these ones green, and now we have our x squared. If you can see the x squared, perhaps you could color code what the x looks like in a different color. Awesome. I see we're going with red here. All right, someone turn on your microphone. How do you see x squared? How do you see x? And why on earth do we need to divide by 2? Let's see, who can rephrase for us? How do we see the x squared? How do we see the x? And why on earth do we have to divide by 2?
Well, again, the x squared is just giving us a square. And the x is just going to give us a column of the same height. So you're going to take the square with a length of x, and you're going to attach to it a column with length of x. And then you got to divide by 2 like we were saying before. We've got a rectangle. We're going to turn it into stairs, which are basically the triangle. So we've got to half it.
Awesome. Let's apply that new knowledge. Come on down to slide 13. We have room for people to draw that extra column. Where do you see that extra column now? Does it look like a column? Does it look like a row? I'm going to let you all keep thinking about that one. And let's move down to slide 14. We've got one more to look at here. So we've been talking about so far how these different formulas are actually the exact same thing. They are all equaling the same thing. And here we've got this fractional one, 1/2 x squared plus 1/2 x. And the people in group 5 did a nice job of visualizing it for us over here. Can you guys walk us through, and you can use the decimal version or the fraction version?
Yeah. Basically, what we were looking at was that it's the total number of blocks is kind of the area of this shape, and it's got, you know, multiple parts growing. It's got the top rectangle, which has kind of an x on both sides. So as x increases, both sides will increase. Whereas the kind of bottom rectangle is, you know, one of the sides is just 1/2, so it will stay constant. So it will only increase in size linearly, whereas the other one will increase, I guess, quadratically, or, you know, to a squared power. So we came up with that formula from Desmos, and then basically kind of tried to visualize, well, the number of 1x1 blocks in this rectangle over here is that.
Very cool. And they actually split their 1/2 differently. Some of you all split it diagonally, some of you split it horizontally, and some of you split it vertically. So now what was the whole point of this conversation? Let's take a look real quick. On slide 14, we have a formula with fractions. On slide 13, let's see. On slide 15, we have a formula with not really a fraction, but the whole thing over 2. And on slide 11, we have 2 different formulas. The 2 red arrows are pointing at them. And anyone who teaches either early algebra concepts or algebra concepts know that students struggle with that idea of which terms do I combine? Why are these 3 different expressions equal to each other? And if we go through the conversation to talk about, well, they're equal to each other because of the visual, some students will buy into that visual before they ever buy into the symbolic. And when we can bridge the 2, we're really bringing in that conceptual understanding. So again, whether you are teaching the younger kiddos who are just learning things like terms, or you're teaching the older kiddos who are talking about generalizations and patterns as they grow, I hope that task can be really accessible to you with minor tweaks. Join me down on slide 17. Slide 17 should look familiar to you from yesterday. If you're looking for a more organized way of putting this one together, you might consider the organization of that. And if you're looking for just more ideas of how this problem might appear if students are putting their work up, you can always check out slides 19 through 22. I've got other student work samples for you to look at and kind of contemplate. And tomorrow we are going to jump right back into this problem, and I'm going to have you kind of do a next day. So if you did this on day 1, what would the warm-up on day 2 look like? And I hope that you continue to think about this problem, and that this problem isn't, how you should say, like finished. It's still perplexing you a little bit. It's still kind of bothering you a little bit. You're still thinking about it. And that's where I'd like to leave you as an educator. I like to leave you in a place of wonderment and thinking. All right, folks, so that is today. I'm down on slide 25. I will take any questions you all have. I hope that your brains keep thinking, and I will see you all tomorrow. Happy online learning. Someone's seeing the connection to Pascal's triangle. That is a fun one. I'm going to leave that on the virtual parking lot, and I'll have some visuals for you tomorrow. Keep thinking about it.
Yeah, that's the. I have to think about that one a little bit.
Yeah.
It's going to be because that's like because Pascal's triangle used that in statistics to count outcomes, and now it's like all connecting to my subject.
And also with Pascal's triangle, try to think of it as probabilities like on a Plinko board, and that normal distributions, and try and stretch outside of the typical triangle visualization and think about it more linearly, and I bet you'll see the connection.
Okay. All right. Cool.
All right, folks, I will see you all tomorrow. Happy online learning.
Thank you, Dr. Wills.
I'm just having a great time doing these. Thank you.
Oh, awesome. All right, catch you later.